All right, so today we're basically gonna be detectives. We're going on a quest to figure out the fundamental building blocks of, well, everything. We're cracking open the case of the atom, and we're gonna start with the most basic question of all. I mean, that's the big one, isn't it? If you could just keep zooming in on your hand or your desk, past what your eyes can see, past what any microscope can see, what would you actually find at the very bottom? This single question has fueled a massive scientific investigation for centuries, and today we're going to follow the clues. So our detective story really kicks off way back in 1808. Our first suspect for what an atom looks like comes from a scientist named John Dalton. He imagined the atom was just a simple, solid, indivisible sphere. Like a tiny, unbreakable billiard ball. That's it. Now, Dalton's idea for its time was absolutely brilliant. He suggested everything is made of these little particles, that all carbon atoms are exactly the same as all other carbon atoms, and that they combine in these nice, neat, predictable ways. It was a fantastic start. But, as any good detective knows, the first suspect's story is almost never the whole story. And yep, sure enough, the case of the indivisible atom started to crack wide open. New evidence started popping up, and it suggested that these tiny little spheres, well, they weren't so simple. It turns out they were actually made of even smaller parts. Scientific discovery is usually a marathon, not a sprint. And you can really see that here. This didn't happen overnight. Over about 35 years, our investigation uncovered 3 huge new clues. First, we find this tiny negative thing called the electron, then a much heavier positive thing, the proton, and finally, the neutral neutron. All of a sudden, our simple little billiard ball has a whole cast of characters living inside it. And that, of course, led to the next great mystery. Okay, fine, we've got positive protons and negative electrons, but how do they fit together? Are they just, jumbled up in there like a bag of marbles? Or is there some kind of order to it all? This question led to a whole lineup of new suspects for what the atom really looked like. So this brings our investigation to the next phase, the sketches. With this new evidence of subatomic particles, scientists basically turned into police sketch artists. They started drawing up models, trying to create an accurate picture of the atom's inner structure. So here are the 2 main early sketches. On one hand, you have J.J. Thomson, the guy who found the electron. He proposed this plum pudding model, which is kind of like a ball of positive goo with the negative electrons just stuck in it. But then, Ernest Rutherford's incredible gold foil experiment just completely blew that idea out of the water. It led him to his nuclear model, where he realized the positive charge wasn't a goo at all. It was packed into a tiny, dense center, the nucleus. And this was the absolute bombshell from Rutherford's work. The solid world we touch and see is, at the atomic level, almost entirely empty space. I mean, to put it into perspective, if the nucleus of an atom was a marble in the middle of a football stadium, the electrons would be like tiny specks of dust flying around in the nosebleed seats. This realization completely changed how we think about matter. But there was a huge, huge problem. According to the physics they knew at the time, an electron orbiting a nucleus should constantly be giving off energy, and it should spiral down into the center in like a fraction of a second. So if Rutherford was right, every atom in the universe should have collapsed on itself billions of years ago. His model just wasn't stable. The case needed a hero, and that hero's name was Niels Bohr. He came along with this brilliant fix. He said, what if electrons aren't allowed to orbit just anywhere they want? What if they're stuck on specific, fixed energy levels, like trains on very specific tracks? And just like that, with one idea, he solved the stability problem. Bohr's big idea was these energy shells. He proposed that an electron in one of these shells has a fixed amount of energy, and it just can't spiral inward. It's locked in place. And each shell, starting with the one closest to the center, can only hold a certain number of electrons. The number is decided by a really simple formula, 2n squared, where n is just the number of the shell. It was this one idea that brought order to the chaos inside the atom. Okay, so now that we have a working model of what an atom looks like, we can use that structure to build an ID system. How do we tell an atom of gold from an atom of oxygen? Well, it all comes down to what's going on in the nucleus. Think of an atom's nucleus as having a totally unique fingerprint. The most important part of that fingerprint is the atomic number. We call it Z, and it's just the number of protons. That's it. This number is the element's identity. If it has 6 protons, it is always carbon. 7 protons is always nitrogen, no exceptions. Then you've got the mass number, or A, which is just the total count of everything in the nucleus, protons plus neutrons. Now, our investigation can get a little tricky because you have these atomic lookalikes. Let's break this down real simple. Isotopes are just different versions of the same element. That means they have the same number of protons, same atomic number, but a different number of neutrons. Isobars are basically the opposite. They're atoms of different elements that just happen to have the same total mass number. So we know the atom's structure, and we know how to ID it. But why do some elements, like sodium, react so explosively, while others, like neon, don't react with anything at all? The secret to that mystery isn't in the nucleus. It's all about how the electrons are arranged. We can actually map out where every single electron goes by following a few simple rules. Step 1, find the atomic number. That tells you how many electrons you have to find a home for. Step 2, you start filling the shells from the inside out. The first shell can hold at most 2 electrons. Step 3, the second shell gets up to 8. And you just keep going, filling up the shells until every electron has a place. And here it is. This is the crucial clue to basically all of chemistry. It's the electrons in the outermost shell, the valence electrons, that decide an atom's entire personality. They control how it bonds with other atoms, what it reacts with, everything. If an atom has a completely full outer shell, it's stable and happy, kind of aloof, like a noble gas. But if its outer shell is nearly empty or nearly full, oh, it is desperate to react with something to fix that. So, our detective story has brought us all the way from a simple, solid little ball to this complex, miniature solar system that's governed by these strange quantum rules. We figured out how to build the atom. But that leaves us with one final massive question. A question that would kick off the entire next era of physics. What happens when you finally crack open that nucleus and split the atom itself?